Okay, this is the last lecture of the school year, right here.
Yeah.
Woo.
Go.
Oh, I know. Come back next year. Take AP Physics. I'll give you more. It's good stuff. Okay. But anyway, take a look. Now, we're going to talk about a couple of physics concepts. 2 out of the 3 are going to be review. One of them is going to be brand new. And then we're just going to solve a few problems, the kind of problems that the Apollo engineers and pilots and astronauts had to solve. And now, basically, in an Apollo mission, and Apollo 15 certainly had this, you had to do several things just right. You had to get from the Earth to the moon. Now, the first thing you had to do was launch into space and get into low Earth orbit. Low, meaning relatively close to the ground. Only a couple of 100 miles up. Now, when you think about the size of the Earth, when you can be in orbit only a couple 100 miles up. That's where the International Space Station is. I think it's about 230 miles high. And you have to go fast enough so that gravity can't pull you to the surface. So you're in orbit. So the first thing the Apollo spacecraft did is it got into orbit. And they did an orbit to check out the spacecraft. They say, is everything good? You know, nothing's broken, all the electrical systems, everything that they could figure out about their spacecraft, they did. Now, to be in orbit, you have to go just the right speed. Okay? And so they wanted to go as slow as possible and still be in orbit because you use less fuel that way. Then once they, and that's called orbital velocity. V orbital. And that's just the speed you need to go to be in orbit. Now this is for the Earth, right? And then they fired their rockets for about 7 minutes. They fire their engine to speed up, to reach what's called escape velocity. Now, you've all heard the expression, what goes up must come down? Yep. That's true, unless you go 25,000 miles per hour. If you go up at a speed of 25,000 miles per hour, you'll go up and you'll never come down. You'll escape from the Earth. And if you go faster than that, you'll just escape from the Earth even faster than you need to. So if you want to get to the moon, you have to reach what's called, right here, V escape velocity. You need to go fast enough that Earth's gravity is still going to slow you down. But what happens to gravity as you get farther from the Earth? Gravity gets weaker, right? So if you go just the right speed, yes, gravity slows you down, but gravity gets weaker. And so you never quite stop. Gravity is not strong enough to stop you. You're always going to be moving away. And even as you're being slowed down, the rate at which you slow down goes down, and you never quite stop. But if you just went that fast and approached the moon, you're going to go too fast to be in orbit around the moon. So you've exceeded the escape. You're going faster than the escape velocity for the moon. So what do you have to do? If you want to be in orbit around the moon, you've got to slow down. So the Apollo program, the Apollo spacecraft, had to slow down, had to fire one of its rockets for several minutes and slow itself down so that it could go into orbit, around the moon. And it did, only about 60 miles up. It was a very low orbit. But there's no atmosphere to speak of. There's a slight atmosphere on the moon, but it's nothing to worry about if you're in orbit. And then the two spacecraft, the command service module and the lunar module, they separated, as we saw in the video, on Apollo 11. And the lunar module went down, landed on the moon. Had to slow down, right, because it's going orbital velocity. You hit the surface of the moon going orbital velocity, even for the moon, you're going to make a big crater. Okay? And they would call it probably, well, there's Armstrong crater and there's Aldrin crater. They'll probably name the crater after him. but obviously they didn't make a crater. So they slowed down, they fired their engines, landed on the moon. They took a little walk, only about 2 hours, 2.5 hours. Aldrin and Armstrong walked around on the moon. They laid out a few experiments. They got back in. They took a nap. Then they got up the next day. They got the spacecraft ready and they flew home. Very quick trip. Because Apollo 11 was all about seeing if we could do it. Then we landed with Apollo 12. They practiced what's called a pinpoint landing on Apollo 12. Then Apollo 13, you know about the accident. The service module had an explosion and crippled the spacecraft. They were able to survive, come back home. That was good. Apollo 14 landed successfully and carried more scientific instruments. And they went on, I believe, 2 extended spacewalks. So I think the astronauts spent a total of about 8 or 9 hours on the surface of the moon. Then came Apollo 15, and you just watched the Apollo 15 video. Apollo 15 was the first real camp out on the moon. I mean, they spent a couple of days on the lunar surface. They had that lunar rover. They were able to drive around. They did extensive science. Dave Scott, the commander, they found that rock that turned out, they call it the Genesis rock. It's one of the oldest rocks from the moon. Original crust. And so it was a great success. Then the ascent module, well, if you draw a picture, let's say here's the surface of the moon, right? So you got the descent module. Oh, you got the descent module. Here's the landing pads like this. One of them's got it's got some struts on it or whatever. One of them's got a ladder on it that goes all the way up here. And now this is called and it's got an engine right here. Now, this was called the descent module, and it had 2 purposes. It had fuel tanks inside here, and it landed them on the moon. But it also acted as a, here's kind of the basic lunar module, had little triangular windows. Kind of neat. It looked like it had a face to it. And then here's the little porch thing. And then it had a fuel tank out here and little thrusters and an antenna, pointed towards the Earth and all this kind of stuff hanging on it. Look at this spacecraft, how unaerodynamic it is, right? It's got stuff sticking out all over the place. You could never build a spacecraft like that, to land on Earth, right? Because on Earth you got wind resistance, and it would just tear all that stuff away. It'd be very, very unaerodynamic. On the moon, you don't care. You can make a spacecraft look like anything you want because there's no air. So there's no drag. So, it was kind of a lumpy looking thing. Then this thing acts as the descent module acts as a launching pad, because in the interior right in here of the ascent module, it's held on by these bolts. They're called explosive bolts because they have little explosives in them. When you hit a button, the explosives explode and they basically break those bolts. And this thing is free to launch into space. And it went back into lunar orbit where it docked with the service module. The command module and service module. The service module had its engine on it. It fired, gave it escape velocity from the moon, headed back towards the Earth, separated, and then they re-entered the Earth's atmosphere in just the command module. Everything else was discarded. So here are the 3 things I want you to know how to do. How fast do you need to go to be in orbit? And how fast do you need to go to escape from any object that you want? What's the escape velocity from the moon and the Earth? One of them's really easy to figure out. So let's talk about, let me zoom out. Let's talk about orbital velocity. Orbital velocity is easy. We did this before. Let's say you have a planet, right? And if you have an object above the planet, like here's a spacecraft and here's the Earth, then you've got a force of gravity pulling you down. And if you're just sitting there, if you're not moving, you're just going to go, You're just going to fall straight down to the earth. But if you've got some velocity like this, well, then you're going to go splat, all right? Well, if you just go faster, if you go fast enough, gravity's going to pull you down. But what happens to the ground? Well, I got news for you. The earth is round. Yes, there are people out there who still believe the earth is flat. Okay? Sorry, it's not. We live on a great big ball. And so as gravity tries to pull you down, the earth curves underneath you, and at just the right speed. If you're going a little faster, what will happen? If you go too fast, you'll go like this. You'll be in what's called an elliptical orbit. You'll still be in orbit, but you'll go up and down, up, like that. But in a circular orbit, you go just the right orbital speed for a circular orbit, your path will look like this. If you go too slow, you'll spiral down and you hit the atmosphere and then you're dead. Or not dead. Sometimes you want to do that, right? You got a heat shield, and so you want to come home. But if you're in orbit, that's what you got to do. So, well, this is the force of gravity. And remember, I said the force of gravity is equal to G times big M. What is big M? The mass of the earth. What is little m? Mass of the spaceship, or you, or whatever's in orbit. Over R squared. What is R? The distance from the center of the earth out to the orbit. So it's the radius of the earth plus our height above the surface. Okay, now we did this before. Does this look familiar? Yeah. Okay. Then I say, hey, but this force, look, I'm moving in a circle. If I'm moving in a circle, what kind of force makes things move in a circle? A centripetal force. So we set this equal to the centripetal force. Well, here's my mass m, v squared over r. That's the centripetal force equation. And look, the mass of the spacecraft cancels out. It doesn't matter how big or small my spacecraft is. If it's in circular orbit, it's going to have the same speed. This cancels that. Just take the square root of both sides. And v orbit equals the square root of gm over r. This is easy. This is one of the three equations you're going to need to know. Well, you do need to know Newton's law of gravity. But this is the orbital velocity equation. Okay. Now, I'm going to talk to you next about the escape velocity. Oh, but before that, let's write down a few things. G equals 6.67 times 10 to the negative 11. Is that right? 6 point? Yeah, that's right, 6.6. Newton meter squared per kilogram squared. This is the universal gravitational constant. It's a measure of how strong gravity is. And gravity turns out to be very weak. Times 10 to the negative 11. Gravity's very, very weak. Look at this pencil. This pencil has mass. I'm attracted to that pencil. I don't really feel it, though, because it has so little mass and I have so little mass. But there's a whole planet of mass under my feet. That's enough mass where the gravity really adds up, so I feel weight. Okay, so you need a lot of mass in order for gravity to be significant. And that's what this number means right here. That number's so tiny. Okay, so what we're going to, and then m. What is m? Is the mass of the Earth or the moon. Remember, we're going to talk about the moon as well as Earth. Okay. Now, what we're going to do next is going to talk about escape velocity. But before I can talk about escape velocity, I need to derive an equation for you for the gravitational potential energy. It's not, I'm going to go through it very quickly, and I'm going to go through it next. So I'm going to split the videos up here. So